So this is Griffiths Electrodynamics problem 2.27. Kind of a messy algebra problem, but what we're going to be looking at first is the potential at this point z due to this finite cylinder of length L with a uniform volume charge density of rho and a radius of big R. So let's draw a few of those things in there. Here's R. So we're calling 0. Excuse me. We're calling 0 here at the midpoint of this cylinder. So it will come out here to minus half of L and go out to plus half of L. All right. It has a radius of R. And yeah, the volume density, charge density of rho. Okay. So our strategy here is going to be, we're going to slice this up into little disks. All right, and then just like in part C of problem 2.25, you can find, let me see. Yeah, so the potential due to this uniform surface charge in a disk. Pretty sure that's the problem. Anyway, basically we've done it before. So so let's do it again really quick. Let's see, I'm going to just draw a disk here, radius big R, and I'm going to use x as the distance up to this point because later on we'll be using x as the distance from our whichever slice we're taking out to this point z. All right, so our differential charge element is given by the surface charge density of this disk, and then multiplied by an infinitesimal area, which is r dr d theta. Okay, so our potential is just going to be 1 over 4 pi epsilon naught, and we are going to be integrating over the whole area, so from 0 to 2 pi for the theta, and from 0 out to r for the radius. Our dq here, we have a sigma r, and then we'll put the dr out here with the d theta. And then we have this cursive r thing down on the bottom, which is just, if this is the little dq that we're looking at, then that's the distance from this source point here out to this field point, which is just x squared, as well, it's the square root of x squared plus little r squared, because that's the whatever point we're at as we move out towards the outer rim, all under a square root. All right, let's write this down here. Bring out our 4 pi epsilon naught. The angular integral is really easy. There's no theta inside this integrand. It's just a d theta out to 2 pi, so that just gives us a factor of 2 pi. Our sigma is just a constant, it can come out. And we're left with an integral from 0 out to big R of little r over x squared plus r squared under a square root dr. So I'm going to go ahead and make the substitution of u squared equals x squared plus r squared. Finding our differential, we get a 2u du is equal to 2x dx. Oh, sorry. Scratch that. X is just a constant in this particular case. Later on it will be the variable, but in this case r is the variable. So we have a 2r dr, and then this is a constant, so the derivative is 0. Canceling our 2's, we get this u du is equal to rdr, and we can just plug this rdr in for this rdr up here, and write this out again. So we have a u du on top, and then this down here was just a u, right? Because we had our u, take the square root of both sides of this. So this is just a u on the bottom. So we just have another simple integral, right? We just have to plug in our limits of integration real quick. So if we put in a 0 for r, then we get, let me go ahead and take the square root of both sides of this real quick and make it easier. So putting in a 0 here, we just get the square root of x squared, which is just x. And then up at the top, we put in a big R, so we get x squared plus big R squared under a square root. This is getting messy. Let's write it more cleanly. Down here, we'll just do the integration. 4 pi epsilon naught 2 pi sigma. And now our u's divided out, we just are integrating du, so we just get x squared plus big R squared minus x. All right, and if you check the limits of integration as x gets much larger than r, we did this in that previous problem, 25, I think, is that right? You have to use a Taylor expansion, or we did the binomial expansion to get the same thing, right? And you'll see that this reduces down to the potential due to a point charge at distances far from the disk. At any rate, this is the potential caused by this disk of uniform charge. Now we have to put it into this case where we are going to be integrating, we're going to be basically adding up the potential due to an infinite number of infinitesimally thin disks that make up this cylinder. First, let's just, let's see something real quick. So we can look at units really quick to see what do we do with this sigma now that we need to translate it into rho. So rho is coulombs per meter cubed, and well, anyway, we're kind of doing units here, whatever. It's not really, anyway, whatever. I'm using SI units. And then sigma is the coulombs meters squared. And so if we have a rho multiplied by a dx, anyway, what we get is sigma equals rho multiplied by a dx. So this is, you can just check that with these units. The dx carries units of meters, so there you go. All right, so the reason I did this is because this gives us our differential that we can integrate over. So V total, or for the cylinder or whatever, let's write out our integral. I don't think I'm going to actually do this integral. I think I'm just going to look it up, Wolfram Alpha or Mathematica or something. Right. So we have our 2 pi, and then we have our sigma, which we're going to put in a rho dx. We'll put the dx at the end, so we'll just have our rho right here. We'll be integrating. We have an x squared plus r squared under a square root minus x, and now we put in our dx. Our limits of integration, So what is x when we are at this side? Well, that is this distance z plus distance L halves. And when we're over at this end, this will be a distance z minus this L halves, because then we're, if I draw in this, then we're just looking at, from here to here, so shorter, right? Or here to here. So let's go ahead and integrate from the small to the large. So we'll start at this point and move out to the longer, out towards the far end. All right, so what did we say? We had a z minus L halves for this short distance here, and then for the long distance, a z plus L halves. So here's our limits of integration. All right. So yeah, to save time, I'm just going to look up this integral and be back in a second. All right, so here we have the integral written out. It came out to 1/2 multiplied by the quantity x times the square root of r squared plus x squared plus r squared multiplied by natural log of x plus square root of r squared plus x squared, and then a minus x squared, and that's it. So you can see that there. Now we have the distinct honor and pleasure of plugging in these ugly looking limits of integration. Maybe maybe we can do something about this. I don't know. Should we come up with a substitution for L over 2 so we don't have to write that so much? I don't know. Yeah, let's do that. Let's just call L over 2 big A or something. I don't know how much this will actually help, but every little bit might help a little bit. All right, so I'm still going to keep my 1 over 4 pi epsilon naught out front. And then we just have a pi times a rho. So I'm just taking this 1/2 and putting it in there. Now here we go. Fun, fun, fun. Nice messy algebra. What am I even substituting? I'm substituting this in for x. So we have a z plus a. And then we have an r squared plus, we have a z plus a. This is a big A. Squared all under the square root. Let's go term by term and plug in these limits of integration, just to kind of keep the similar terms together. So now I'm doing this, plugging this lower limit of integration into this first term. So now we have a z minus a, and then this square root thing of r squared plus z minus a squared. All right. Now plugging in the top, our upper limit of integration into the second term, we have to start way over here because we'll probably need the space. R squared. Let's write these two limits of integration. We'll use the natural logarithm thing to just make it a fraction. That will save us some horizontal space down here. So up on top, we've got z plus a plus this r squared plus z plus a squared under a square root. And on the bottom, we have a z minus a plus, we have an r squared plus z minus a squared under square root. And then we get, what would this be? A minus z plus a squared. And then we'll end up with a plus z minus a squared. Okay, and then we just need our closing brace. So here we have the total potential due to this cylinder. I'm sure there are ways to simplify this. I'm not going to worry about it at this point because we may have to actually simplify it for our, because next we're going to be calculating the electric field, right? And for that we need the negative gradient of our potential. So at least this is only in one dimension, right? So we're only talking about z. I guess we'll call this, since z is the variable that we have left in our potential here. So yeah, so we'll be taking minus the derivative of our potential with respect to z and in the z hat direction. We don't have to worry about any of the other two dimensions, so we've got that going for us, which is nice. So now, here we go. Let's see if we can do this. I don't know. I'll probably make some mistakes and come back and fix them. But, oh, by the way, E is a vector. I'll put a little arrow over the gradient too, which is a vector operator. All right. So we have a minus sign out front. We'll have our pi rho over 4 pi epsilon naught. And let's go ahead and put our z hat vector out here too. Okay. This is going to be a huge mess. I'm not sure if we have time to go through all this, but okay, we'll start right here with this term. Okay. Right, so here you see how far I got before I gave up. Here's, I started making mistakes right away, blah, blah, blah. Just, you can plug this into Mathematica or something and simplify it. So here's a simplified answer. Probably not worth your time to mess with all that algebra unless you really enjoy it, or unless, yeah. Anyway. So let's go ahead and put this back into the terms of our problem. So I'm going to reverse our substitution where we used L half. We changed that to A, so let's change it back to L over 2. And let's go ahead and factor out a 2 as well. I'm still going to leave this as 4 pi epsilon naught here on the bottom. You can, change it if you want. 2 pi rho, so factoring out this 2, right? Okay, so now we just have an r squared plus z plus L over 2 squared under a square root. And then we have, let me come down here, we have a minus r squared plus z minus L over 2 squared under a square root. Okay, and then we had, we factored out a 2, so this is minus 2a now, so that's a minus L over 2. Minus L over 2. All right. So here's our answer. We need our z hat vector as well. So yeah, you can see that huge mess, which I probably didn't even write correctly. It does simplify down into something that's fairly reasonable, but I'm not a very big fan of this problem because typically, with all that algebra, I'd simplify it in some way that actually made this more complicated, or I'd make some mistake somewhere and it would just not turn out right. So I would definitely, unless your instructor says you're not allowed to use Mathematica or something, I would definitely go the route of simplifying it with a computer or some other way. But anyway, so here's our answer.